All right, well, good morning. Yeah, appreciate y'all coming in this morning. Going to talk about reality capture this morning. It's I know there's kind of go through it, but there's a lot of buzzwords out there in the survey and the geospatial industry these days. I'm sure that you all have probably seen projects touched by Lidar and reality capture in some shape. I thank Ian for the great introduction, so I'm not going to dwell on what I do. I've been a surveyor in Florida for a lot of years and have had the luck to be involved in some really great projects. I'm going to try to highlight a couple of them for you today. We have a couple case studies we're going to go through, but a little bit about ETM surveying and mapping. We were originally founded in Jacksonville in 1924 as Robert M. Angus and Associates. We were consequently acquired in the mid-'80s by England-Thims and Miller, an engineering and design firm up in Northeast Florida. The survey group is a standalone company. We presently have a little over 90 employees, 5 licensed professional surveyors, 12 FAA Part 107 licensed pilots, and we operate out of 4 offices. So I wanted to start off right off the bat, a little idea of what reality capture can look like. So this is an interchange, one of the case studies. I'll get into the details a little bit more. It's called the Deering Park interchange. It's interchange with I-95 and State Road 442, which is probably about, 40 some odd miles east of here over on I-95. It's a section of roadway that we utilized reality capture on. We utilize both terrestrial scanning as well as aerial LiDAR on this. So we fused the 2 data sets together to be able to extract a contiguous model, and that's part of the fun. So just to kind of show you what some of the details of reality capture, let's wake up a little bit. So. This is all point cloud and CAD file that you're seeing here. All right, so that was basically just a fly through with the 3D point cloud, the CAD file overlaid, and to get into some of the details we're going to talk about today. Say what's the buzz? Like I said, the geospatial industry has really been bombarded over the last few years with a lot of acronyms. Digital twin, reality capture, data fusion, point clouds. So just kind of, I know everybody has their own idea of what those probably entail, but just to kind of define what I'm operating within for today, we'll go through kind of some details. So a digital twin is strictly a virtual representation of a physical object, process, or system. So it can be a lot of different things. It's not just into one pocket. I kind of jokingly say it's kind of whatever the client wants, they can fit it into one of those three areas. Reality capture, a process that uses technology to record and capture the physical world as digital data. So again, think point clouds, 3D. Data fusion, with the multitude of sensors that are out there. There's multiple Lidar sensors, terrestrial, aerial, mobile. There's actually wearable, which we'll talk a little bit about. But there's also thermal, infrared, different types of data that can be integrated and fused together. So the data fusion process is the process of integrating data from multiple sensors and sources to enhance the understanding of a project and to improve decision-making by stakeholders. And then a point cloud, simplest form, it's strictly a collection of 3D points in a 3D coordinate system. So think X, Y, Z, and some metadata. Why would you want to use these technologies on your projects? Well, a lot of reasons. I think number one is the faster data acquisition, improved accuracy, and reduced costs. Those top three really speak to what you as engineers and as what your clients can achieve. Time is money. The faster that we can turn a survey around to you for your design purposes, the faster you're going to be able to get your product out, the more money your client's going to save. Also, it enhances collaboration with the introduction with internet, portals, 3D CAD files, point cloud files. There's a lot of interoperability that you can utilize, which I'll show you a little bit of with one of our portals that we used for a project to enhance collaboration between the various professions. And then also increased safety, not only for the, in the case of transportation projects, the motoring public, but also the workers that are actually out gathering the data. There's, a lot less need to be in or near the traffic zones. To get into a couple of the case studies, so the Deering Interpark Interchange, which you just saw, that was a collaboration with the Deering Park Stewardship District, the FDOT, and the City of Edgewater. And the project itself was roughly, as you saw, I think it's about 2,600 feet, or roughly about a half a mile of I-95 main line, and then about the same on State Road 442. There's an overpass. So we utilized traditional kind of terrestrial scanning. Terrestrial scanning's been around for a long time. It's pretty much the gold standard, very, very accurate, and very easy to work with the process and work with the point clouds. But we also, this is part of a larger project for us, where they're also going to be doing a lot of development work. So we also needed some information in the 4 quadrants, which is why we had decided to fly the project. So we flew State Road 442, and then the quadrants, and then we did terrestrial on the main line, and then just brought those 2 data sets together to create our final model. Now, what you have here is one of the, you'll see in our aerial system, we fly photogrammetry at the same time as we gather our Lidar data. So we have, day of data collection photography of the area. So this is just the ortho photo overlaid with the some of the CAD file details of the roadway. But I also wanted to show you if you can kind of see a little bit of change here. That's the detail of a 3D point cloud that's colorized, overlaid with the same CAD file. You can see a little bit more richness in the color, a little bit more dimension to it. You can also take these, in the CAD environment and be able to, create some oblique shots. So you have a lot more, ability to showcase some of the aspects of the project with your client. Now, this particular shot, it's quite busy, and you can kind of see in the background up at the top of the slide, there's a lot of power lines. There's transmission lines going through there. There's also a pedestrian bridge that crosses State Road 442 in the background. See cell towers. I mean, just a lot of data. And this is all data that was picked up basically with just the aerial system. And as I think you saw in the video, one of the things that impressed me is we do a lot of tree surveys and tree inventories, especially with transportation projects. And you could pick out every tree with dimension and size as you're going down the roadway in that fly through. So it's very easy to ID. So that was the interchange project. One of the other projects that we were involved with over the last year was they called the Stadium of the Future. I don't know if you all have heard that buzz term or not, but it's a Jacksonville term. It's for the Jacksonville Jaguar Stadium. And it was a public-private partnership between the city of Jacksonville and the Jaguars to renovate the stadium. There's also a big push with Shad Khan and the ownership of the Jags to develop the area around the stadium. It's called the Shipyards Project, which again you may have heard of. So the stadium is just one part of the overall development scheme, but the city had a grand vision for the area and for the stadium itself. And I don't like reading slides, but this one I thought was good. It's just the Stadium of the Future represents a bold and visionary step in the evolution of the Jacksonville region. Jacksonville is poised to become a leading destination for sports and entertainment, offering an experience that will set new standards for stadiums worldwide and in turn drive business growth and investment in Northeast Florida. So this is really a big undertaking. You can see they're putting a lot of money, a lot of effort into this, not just the stadium, but renovating the entire downtown area and bringing it back to kind of an area where people want to come and not only just to see a football game, but there's concert venues, there's baseball venues. It's something. The thing that we got, we did win the survey for this project. The entire project on the Jaguars timeline was to minimize the stadium closure. So they wanted the survey, the design, and the renovation done basically within about 2 years. We started right at the end of their last football season in January. We had access to the site. It was about an 80-acre campus. I'll have a map of it. We'll kind of go over it, but it created a lot of challenges, not only the timeline for turnaround, but also just the massive area that we needed to survey and what the details that we needed to get around the stadium for the architects and the engineers to do what they needed to do, created a lot of issues. And so we pretty much emptied the toolbox. We settled in our aerial Lidar, mainly for the stadium field and then the parking areas, the large part of the campus. But there's also areas around the base of the stadium where our aerial Lidar could not get to. Think the drip edge and kind of underneath a little bit. So we utilized terrestrial Lidar there. As we worked through our scope, the architects and the engineers asked us for some additional, call it scope creep. They needed some additional information, which I'll get into. So we utilized a newer technology, which is a wearable Lidar unit that utilizes SLAM, which is simultaneous location and mapping software. And I'll kind of explain that here in a little bit. But then we also utilized our standard tools of RTK, GNSS for the underground utilities and for establishing our primary control, digital levels for vertical control, and then total stations for traverses. So to get with what does the stadium look like? This is the campus. You see everything you see on the map there is the campus. Only the colorized areas were the areas where we were working. The area that you see up in the upper left-hand corner, that's what we call the Mill Electric practice field, which was a project that we had already finished with the Jags. And that was pretty much exempted out of this part of the design anyway. But you see it's, like I said, roughly about 80 acres. We had to deal with multiple venue sites here. You see the area to the south or the lower part of the slide in white that's not colorized. That's a concert venue. And then off to the left, where you see the parking area that's not colorized, further to the left is a baseball field. As well as the stadium had, even though the football season was over, they had venues or events at the venue coming in. They had concerts and I think they had the monster trucks and other things that were coming in. So we had to work around all of those activities as well as get into the site where it was secured. So we coordinated both with the city security and the Jaguar security via the map. So like I said, we utilized our aerial LiDAR, and we wanted to create a control network that everything would be based off of, so that we didn't want anything that was going to be destroyed during the process of the renovation, so we could always bring back the datum, if you will, that we were operating in. So here you see a layout. We utilized the primary control layout also for our aerial targets for the UAV. We set up a flight path. The whole 80 acres took roughly about 12 or 13 minutes to fly. But I wanted to get some redundancy on the site for a couple reasons. There's a lot of information there that, we fly what they call a double lawnmower. If you kind of think you're crisscrossing this way and then going 90 degrees to it back and forth. So that's the way we fly it. But we also rotated that flight pattern 45 degrees and flew it again. So we had redundancy on the site. We got a much richer data set, but we also wanted to make sure that in case anything went wrong with one of the flights, we would have a backup flight set. As it turned out, everything went well, and we were able to utilize both data sets. On this particular flight path, we were at 300 feet AGL, which is just above the ground level. And at that, we're overlapping roughly about 180 feet on each path. It was I said, a very short flight. We got a lot of data out of it, and everything processed well. So the second part of the process was to establish some secondary control around the base of the stadium. Like I said, we had to kind of get in underneath between, as you see down on the south side of the stadium there, between the concert venue and the stadium itself. That's a large market area, a lot going on. And I'm sure you all have seen NFL or any kind of stadium. There's a lot of piping, a lot of utilities that are exposed throughout the system. So we needed to pick a lot of that data up. So this is a sample of our secondary control traverse. We ended up doing a control traverse like this on all 6 levels of the stadium. And that became part of that secondary scope that came out on the system. Kind of run over the tools a little bit. This is a shot of our UAV that we use. It's a fairly large system. It's a Harris H6 UAV. This is a kind of a breakaway shot of it. It's a hybrid gas-electric UAV, so it has a 2-stroke internal combustion engine on it, which is also powering a generator. The generator charges the batteries run the motors. The black dome that you see on top of the UAV, that's the covering for the gas tank. With this platform and our payload, which is a Regal VUX-1 UAV, a Sony camera, and an Planix IMU, which weighs roughly about 13 to 15 pounds, the entire package keeps us under the 55-pound weight limit, so we're still considered a small UAV. But we get a little over an hour time aloft with this system. Now, obviously, we didn't need it for the Jaguars, but we also use this for what I call greenfield, just large-scale development projects. Think 500 plus acres. We can actually fly, depending on which flight pattern we use, pick up between 250 to 400 acres an hour with this UAV. So it's a very versatile system for us. This is a shot of it getting ready to do a deployment at the stadium. The ground control station in the foreground, you can see one of the flight plans that we looked at up on the screen. It's a shot of our flight crew. We'd go through pre-flight and post-flight checks. The pre-flight, they have to load up the flight plan. They do all their monitoring checks, make sure the data can log properly, that all the operational aspects of the UAV. There's a lot of moving parts, especially on the gas-electric, gas lines as well as electrical lines. Just a lot of things that we want to make sure are operational before we take off and land. Now, I'd mentioned the wearable mobile LiDAR, so this is it. This is the NavVis VLX3 wearable mobile with SLAM. Up on the top halo there, you see it looks like a little puck. That's one of the LiDAR units. Then on the breastplate, you see a secondary one. So it's actually firing around one way, and then it also is firing vertically as well. So you're picking up things on the sides as well. Between each LiDAR puck emits roughly about 1 million points per second. So with the two pucks operational, you're doing 2 million points per second as they're walking through. Below the top halo, or the top LiDAR unit on the halo, there are 4 panoramic cameras that are going in all the cardinal directions. And the operator actually triggers that. You can see his hand on the stabilization tool there. There's also a button there where he fires those pictures. He roughly about every 30 feet they'll stop and fire photos. So what this really develops for us is, in the post-processing, we get what is the equivalent of like a Google walkthrough of wherever we've surveyed. And again, it's day of data acquisition photography. It's a lot of fun. The SLAM part of it, the SLAM utilizes both the photography and the LiDAR to really just think of SLAM as it's really just kind of mashing this stuff together and creating a 3D model on the fly as it's going through. It's looking at like building edges, corners, any type of unique feature. It matches automatically and will build that 3D model on the fly. So the operator, you can see him kind of looking down a screen. It's like a little iPhone, if you will, for a display. So he can see what he's collecting as he's collecting it. So if there's any voids or areas where things are obscure, he can actually see that and go back in and pick that up, day of acquisition again. So there's very few go backs. Another aspect of the project was that we had to locate the existing underground utilities. Now, in this particular venue, because many of you probably aren't familiar with it, presently, before we started the renovation work, there was 3 iterations of a stadium at this site. The field footprint maintained the same footprint through all 3 iterations, but the infrastructure around it changed. With that, a lot of underground utilities were brought in. A lot of underground utilities were abandoned in place. So it was quite a maze. And we were tasked with identifying not only the active utilities, but trying to map out as many of the abandoned utilities that were inactive that we could, just so it would help the contractor when he encountered something, if he encountered something, that he had a higher confidence level of whether it was active or not. This is all considered remote sensed data. It's things that we're measuring remotely. We're not doing with a steel tape in a transit or a total station. So we do a lot of checking. We had to validate the data, and this is what you see here is just some of the validation process of our crews going through with the NavVis unit, where when we did the terrestrial scanning, we set these 4-inch targets. They're black and white targets that the terrestrial scanner picked up. Well, we could see those in the NavVis scan, and we just tag them. We can tag them as a control point. That's what they're doing there, is they're saying this is a point of interest that we're going to locate, and it'll develop an XYZ at that location. So we could compare the NavVis developed coordinate with what our surveyed coordinate was versus what the terrestrial scan coordinate was. It was a very good way for us to compare our data qualities. Now, and I don't want to belabor it a lot, but just the point cloud itself was validated to verify our accuracy and our precision on the units. We wanted to know exactly what we could certify to as far as the horizontal and vertical accuracy. Horizontal, we really didn't have any issues with. The vertical is the biggest. As you pointed out, the vibration, the UAV, you've ever flown in an airplane, it doesn't go straight, it goes up and down. And a UAV that's less than 55 pounds along the St. Johns River, where there's always wind, is not moving steady. So we accommodate that with post-processing and software, but we also want to check it. So in this case, we did a total of 225 points through the area where we utilized the aerial LiDAR, and then 17 points around the base of the stadium where we used terrestrial, and then a total of 77 points on the interior of the stadium. Again, I'll kind of get into that scope a little bit. We haven't talked about it much, but that was with the NavVis. And then all 3 data sets, I know this is kind of hard to read, but the splatter plots that you see there kind of show the story. The one on the right is for the one on the left is for the terrestrial, or for the aerial. There's 225 points. The largest outlier we had was 0.08 of a foot. That was the statistical component that we utilized to measure and validate the data is called the RMSE. It's the root mean square of the error. And in this case, we're showing the vertical component because that's what we're testing. And so most of our data was 0.05 or less. And the RMSE value for the aerial data was sitting right at about 2.5 hundredths of a foot. So you think roughly a little bit more than 1/4 of an inch. So it's just pretty tight data. There wasn't a whole lot of noise in it. The terrestrial data, you see fewer points, but we had one outlier at about 4.5 hundredths. Everything else was 2 hundredths or less. And surprisingly, the NavVis data, again, we had 77 points. We had a few outliers, again, at about 4.5 hundredths, but the RMSE value was, again, around 1/100th, a little bit higher than that. But most of the points were falling within 2 hundredths of what the surveyed values were. So all three data sets, surprising, it was nice to see, really came together well, and we had good accuracy with them. So, talked a lot about the three different data sets. So I put together just a quick video here, kind of showing how the three data sets came together. So this is what you see here is the NavVis work. This was mostly the interiors of the stadiums. We were doing utility closets, hallways, offices. We did a little bit around the base of the stadium. And then that was also a colorized point cloud. Now the non-colorized point cloud that just came in, that was the terrestrial data. I didn't colorize it so you could, just for contrast purposes, so you kind of see where the two data sets overlapped and how they meshed together. And then you're going to see finally the aerial LiDAR data is going to come in, and it's colorized. So there's the model of the three data sets. What we did then is clean them out and, like I say, fuse them together. But it's more than just, you don't just cut it and say, slice it here and put it together. We're actually looking at common areas, looking at the values, making sure that the data matches in well, and then knowing where our boundary is. We create a boundary there so we know where this area we can certify to a certain level of confidence. We can certify to a different level of confidence in this area. So each data set had its own certification to it. After it was all cleaned up, we colorized the entire point cloud, and this was really the model where all of our extraction was done from. The overall model that you see here, 14.5 billion points is what we ended up utilizing for our final model. So it's quite dense. That was thinned out, but we needed to thin it out really for the sake of the computers that we're using to extract from, and also for the end users, that we're going to be using the surface and the files. We had to segment out the data, but it was quite a fun project to work with. It was challenged a lot of data to it. So even though this is all remote sense data and 3D point clouds, what we develop are typically just CAD files. Now in this case, here's a sample of the 2D surface, or 2D of the subsurface utilities that we located. Ultimately, this went to a 3D file after we did our VVH verifications on them, but originally this was just a 2D map. The 3D topographic survey, this is again CAD file. You can see quite busy. That's on the left, you see the overall, and then on the right, there's now the blow up of one of the areas. You can see how busy this area was. There's just a lot of utilities, a lot of information that was transmitted through here. So the surface and the model that we supplied to the engineers and the architects was good, and it gave them everything they needed for their design, but they also wanted some additional work done. And that was, I've talked about the extra scope. And what the ask was is they had identified 500 points throughout the stadium that they wanted XYZ on. They wanted to know the exact location in our grid system, plus the elevation of each of these locations. And these 500 locations were scattered on all 6 levels of the interior of the stadium. Again, some of them were in offices, some of them were in utility closets, some of them were in hallways. So our solution was the NavVis. That's why we utilized that tool on the project. We were able to establish control traverses and elevations at each level of the stadium, walk the NavVis through, and really develop a very rich model of every single floor in 3D with photography as well as the colorized point cloud. So we hosted the data. We gave the engineers and the architects what they wanted, which was basically CAD files of every floor with those locations tagged. But we also generated PDFs. But we showed them what kind of a new delivery method is. I'll call it a digital delivery method, but it's really utilizing software as a service. And what we did is we hosted all of our point cloud data for the interior of the stadium on our Ivion. It's a NavVis platform. It's called Ivion, and it's, again, internet-based, and think Google Earth. It's just you log into it, you load up a system in there, and you can go in and literally navigate through every floor of the stadium from one level to the next, just like you're in Google Earth and just clicking a point. And so the following here is just a sample of what that looked like. So this is the first floor of the stadium. All those blue and white icons that you see were points of interest for them. Those were the areas where they wanted the elevation, the XYZ information on. We also, you see some blue and green points in there too. Those were, so we're utilizing this to really show the city as well as the Jaguars that there's additional uses for their data than for the point cloud that we had. So we tagged some GIS features, and we'll kind of show you a little bit of those. But here's a video I put together of just the navigation through the system. Here it starts in somebody's office, and they'll bring up the navigation screen. Then all these icons are clickable. So they click on an icon, it will transport you to that location in the stadium. And then up in the upper left-hand corner, you see that box populate. That populates with the elevation and the location of that point. You also see there between the elevator shafts is a control point, and then there's a GIS feature just saying that there's an elevator shaft there. And again, you don't have to do just like a walkthrough from place to place. You can go back to the navigation, pick another location. Doesn't have to be an icon there. The point cloud is active underneath everything that you see. So wherever you click, it'll take you to that location. You see the photography here, but behind it, the point cloud is active. So you can get information. You can click. Here you see there's 3 first aid functions. There's a sanitation, hydration, and then a fire hose. And you can, like I said, you don't have to go just where there's icons, but you can also make measurements anywhere within the system. They're cursory measurements. I don't know if I'd use them for your design, but if, say you wanted to check clearances and it wasn't real tight tolerances that you're looking for, plus or minus a ½ inch, you're going to get very good results here. And so just kind of show you they could go in. We didn't collect an elevation at this particular location in the stadium, but you could go in and query it. But you can query a point. You'll see he'll click a point on the floor there. It'll return the elevation, and it'll populate, put a little point there. And then on the right-hand side of the screen, it returns the XYZ of that location. He can also go in. There's various measurement tools. Like I said, you can measure a horizontal clearance between 2 walls. So just clicking the point, it'll snap a perpendicular to the other wall and give you the minimum clearance between those walls based on the point cloud measurements. You can also do the same thing vertically. What happened was that we hosted this and we showed it to the clients, both the city and to the architects and engineers, and they thought that, yeah, we'll give it a shot. We'll utilize it a little bit because most of our designers have not seen the stadium. They've never gone, they hadn't visited the site, but they're designing on it. So this would give them the opportunity. After about 3 or 4 weeks of using it, they contacted us back and said, hey, could we get the whole stadium loaded up here? And could you host a platform that's just exclusively for us? So we did. Started out with 5 users. There's now 80 users every day logging into the system, utilizing it. What it did is it exposed that there's a lot of other data that they hadn't anticipated, unintended consequences. We scanned something, there's other things that they could use it for. They found that there are some structural members that were secreted behind walls. They identified where those were. They went in and demoed them, had us go back in and scan those areas, bring them into the same point cloud so that they could utilize that for part of their design. And so it worked out really well. It was a win-win all the way around, and but really a unique way of delivering reality capture products. So I thought it was a lot of fun. So you heard, again, we started with a fly-through. I figured we'd kind of go through another one. So here's the stadium. Again, you'll see a little pixelation here because it's all point cloud. And then there's a little bit of CAD file in here too, but this is all colorized point cloud. It's not photography that you're seeing through here. So. All right. So I know I'm running a little bit over, so I'll just go real quick, wrap it up. Advantages of reality capture: faster data acquisition, improved accuracy, reducing the costs, enhanced collaboration, increased safety. Those are just the top five I could come up with. I'm sure there's a lot more. So I thank you for your time this morning. The QR code is my personal contact information.